In this example of a beam deflection problem, we have a very simple case of a beam that has pin support at the left, roller support at the right, and a concentrated load in the middle. It's a very simple little situation. We're asked to derive the maximum deflection of a simply supported beam. The problem here is that it's going to turn out mathematically or calculus-wise to actually be quite lengthy, and we'll probably break this video up into several segments. Right, now remember that our governing differential equation is going to be that with constant EI times the fourth derivative of the transverse deflection is equal to the load intensity. And what could be simpler to do? We just integrate this 4 times. And even simpler because the distributed load intensity is 0. All of the deflections here are being caused by this concentrated force. Right, so we might want to guess here what the deflected shape looks like. And hey, this beam is just going to sag under this mid-span load, and we'd have a nice little smiley face kind of shape. Sort of makes sense. Zero displacement at each of the 2 supports. That little simple curve is going to be unfriendly to actually derive. Right? And we want to find actually just the maximum deflection of the whole thing. Right? And the reason why it's so ugly to do is because although the distributed load is 0, that part is simple, but we have that concentrated effect. We have to deal with this in 2 segments, just like you see here in the shear diagram. And we go up by the left reaction, go over at constant 0 slope, and then we get the point load has immediate jump down, where there's no single one equation that does this. Right? If we let the origin be over here at the far left, then our functional description for V, our shear, that is that it's equal to plus P over 2 when X is less than L over 2, and it's equal to minus P over 2 when X is greater than L over 2. Now, already this is a pain to write. Then you come over to the moment diagram, we got the same kind of business going on here. Now our moment function has to be broken up into 2 pieces. The first part is going to be Px over 2 for x less than L over 2. And then for the right half piece, it's kind of a pain in the rear. We know what the slope is. It's equal to the shear. We're going to have a minus P over 2x. We have to get the right intercept. So if we extended it all the way back, right, it was at PL over 4 at its peak, and then it gets doubled over here, so that'd be PL over 2. Looks to me like then our y-intercept would be that. Let's check it out. Put in L over 2, that'd be minus PL over 4 plus PL over 2. That will give us the PL over 4. Put in L, and we get 0, just like we're supposed to. So I think we got that right. And so that would be for x greater than L over 2. We got to come up with those functions. We could do it by observation like I did here, or we could do the formal integration twice and get the boundary conditions and all that kind of stuff along the way. But notice again that we've got 2 separate functions in each case to have to deal with. We've got twice as much work. It's actually a little bit worse than that. So that'll conclude part 1 of our example.